Okay, let's continue. My video usually will automatically stop after 57 minutes, so I try not to let it automatically stop, so I stop by myself. Okay, let's continue. K, if we have 1 square plus 2 square, 3 square, 4 square, up to n square, by the formula, there's some way to evaluate. It is equal to n times n plus 1 times 2n plus 1 over 6. Again, let's try to verify it. This time, let's use some small number. N is 4. When n is 4, let's check. Here's a 4. 4 plus 1 is a 5. And 2 times 4 is 8. 8 plus 1 is 9 over 6. Well, let's see what it is. 4 times 5 is 20. 20 times 9 is 180. Over 6 is a 30. Well, let's see. Let's check. 1 plus 4 plus 9 plus 16. 1 plus 4 is a 5. 5 plus 9 is a 14. 14 plus 16, 30. Very good. So it's correct. Okay, so it's a right formula, at least in this case. It's sure correct. Okay, so this is the formula for this special case, a special sequence. Okay, and all the sequences must start from 1. When we read the formula, the sequence must start from 1. Okay, stop at that. And the next special sequence, the sum of cubed number. K equal to 1 is 1 cubed. K is 2 is 2 cubed. K is 3, 3 cubed. K is 4 is 4 cubed. Up to K is equal to n is n cubed. And this sum, by some effort, we know it is equal to n times n plus 1 over 2. This whole thing squared. This whole thing squared. Let's just verify it. We also verify with 4 numbers. For example, here n is equal to 4. N is equal to 4, so it's 4 times 4 plus 1, 4 times 5 over 2 n squared. 4 times 5, 20. Yeah, 20. 20 over 2, 10. 10 squared, 100. Right? It's 100. And let's check this. 1 cubed is 1. 2 cubed, 8. 3, this is cubed. 3 cubed, 27. 4 cubed, 64. This sum is 9. 9 plus 27 is 36. 36 plus 64 is 100. It's correct. It's correct, right? Okay, so this theorem just tells us for those 4 special sequences, we know the values, the sigma from 1 to n for those different 4 sequences. In general, we don't know the value. Okay, so for example, if I give you k from 1 to n, sine of k, I have no idea what it is. It's just this symbol. It just means a long sum. It means a sine of 1 plus sine of 2 plus sine of 3 up to sine of n. And that's it. That's it. It's just a short way to write this long sum. There's no formula for us to know what it is. Okay? So here, I use this example just to say they are very special. You don't always expect, okay, we have a very good formula for whatever sequence. That's not correct. Okay? So for example, let's try to apply those formulas. So first, sigma k from 1 to 5, 3k. K from 1 to 5, 3k. First, 3, constant coefficient. Remember that the first property is the coefficient rule, constant coefficient rule. When you have constant coefficient, you can move it forward. It's not about the application of the evaluation. It's just about the property of the sequence. Okay, so constant coefficient, we move it forward. We get 3 times k from 1 to 5 k. And now you compare this expression with those 4 special cases. It's this one, and n is equal to 5. So you will let it 3 times n is equal to 5 in this case. So it's a 5 times 5 plus 1, 6 over 2. Okay, so you get it formula and plug in the value of n. N is 5. So 5 times n times n plus 1. So 5 times 6 over 2. 5 times 6, 30. 30 over 2 is 15. 15 times 3, 45. Right? 15 times 3, 45. And second, k is from 1 to 10. And k cubed plus 1. K, it's a sum. Sigma of the sum. We use the sum rule. We distribute sigma notation into the parentheses. Sigma k from 1 to 10, k cubed, plus sigma k from 1 to 10, 1. The first one is exactly the last case, k cubed 1 to n. So k cubed, it fits the function. 1 to n means n is 10. 1 to 10 means n is 10. n is 10. So here you let n be 10. 10 times n plus 1, 11 over 2, and then squared. Okay, so that's the first term. First sigma. And second, it's a sigma constant. We know that. What is a sigma constant? It's just n times constant. Here n is 10, 10 times 1. Okay? And 10 times 1 is 10. And here, 10 times 11 is 110. 110 over 2 is 55. So it's a 55 squared plus 10. 55 squared, you compute it. I guess it's 3025 plus 10. It's 3035. Well, let's compute. 5555. 5, 27, 275. It's a 5203. Yeah, it's good. So it's a 3025. It's a 55 squared plus 10. So it's a 3035. So the answer is a 3035. Okay, so that's his answer. Next. Okay, it's more complex. It's sigma k from 1 to 24. Wow. K squared minus 7k plus 2. So it's more complex than the second example, but it's okay. So you have a difference and the sum. You just distribute the sigma into the parentheses and assign it to each term. Sigma 1 to 24 k squared minus sigma k from 1 to 24 7k and plus sigma k from 1 to 24 and number 2. In the first part, the first term, it's this formula. K squared from 1 to n. It's n plus 1 to n plus 1 over 6. So n is 24. So you get 24, n plus 1, 25, 2n plus 1. 2 times 24 is 48, plus 1 is 49 over 6. That's the first term. Second term, you have a coefficient 7. You move 7 forward. Let's do the problem step by step. So I move 7 forward by the constant coefficient property. And the third one, it's a sum of a constant number, sigma c. Sigma c means it's n times c. So it's 24 times 2. This property, this evaluation, right? Okay, so let's continue. Well, 24 over 6, this becomes 4. 4 times 25 is 100. 100 times 49 is 4900. Okay, so you don't do the multiplication of the numerator first. You do the cancellation first. You cancel 6. You can easily do that. 4 times 25, 4 quarters is a dollar. So 4.25 cents is 100 cents. So it's 100. 100 times 49 is 4900. In this one, 7 is the coefficient. K from 1 to 24, K, that's its formula. So it is 24 times 25 over 2. N times n plus 1 over 2. And plus 48. All right? So it's 4948. So it's 4948 minus. Okay, now this time, let's check. It's 24 times 25. We cancel 2, we get 12. 12 has 3 times 4. 12, 3 times 4. 4 times 25 is 100. 3 times it is 300. 300 times 7 is 2100. Okay, you see what I did? So I first cancel 2, I get 12. And 12, I break it as a product 3 times 4. 4 times 25 is 100. 3 times 7 is 21. 2100, because this is all product. And then you use this number to minus this number, you get 2848. 2848, yes, right. Okay. Next, sigma k from 6 to 20, 4k squared. You see, this problem is different from the first 3 examples, first 3 problems. It's because here the k is from 6 to 20. All the previous examples, k is from 1 to a number. And the formula, in the formulas, k is from 1 to n. So you have to use the fourth property. Remember that, the fourth property. So how do you use it? It is equal to sigma, I will consider it from 1 to 20, 4k squared. But since the original problem starts from 6, it means the first 5 terms we don't consider. So it's a subtraction from 1 to 5, 4k squared. You just consider from 6. So first 1, 2, 3, 4, 5, you're going to subtract. Okay? So that's the pattern. Okay, now let's check. And now you see here, it's a difference, but they are both from 1 to a number n. So here you move the coefficient of 4 forward. K from 1 to 20, k squared. Here do the same thing, you move 4 forward. K from 1 to 5, k squared. K squared, what is the formula? K squared here. N times n plus 1 times 2 n plus 1. So it's 4 times 20 times 21 times 41 over 6, right? N is 20. And minus 4 times n is 5, right? So it's 5 times 6 times 2 times 5, 10, plus 1, 11. Okay, let's try it. Here, some 6, 6 cancel. And this place, this place, 21 is 3 times 7. Here is 2. And then you cancel 2 is 20. So this is 10. So the first is 4 times 10 times 7 times 41. Power is down. Let me finish this. Okay. Wow. It's bad. Okay, anyway, let's continue. It's 4 times 10 times 7 times 41 minus, here 6 cancelled, it's 4 times 5 times 11. Well, you just do the computation, possibly you will get the answer. I'm not going to continue this writing. 11,260. Okay, so that's the answer. Okay, I hope you understand the whole steps. Okay, let me see if we have more examples to practice. Okay, let's try this. In the exercise part, there's such example. The example is not about evaluation, it's about the recursive defined function. So for example, we have recursively defined sequence. Let's check. It's a 47. It's a 47. A1 is square root of 2, and an is square root of 2 plus a sub n minus 1. Let's try to write first a few terms. Okay, now a1 is this. What is a2? a2 is square root of 2 plus a1, the preceding term. N is 2, then 2 minus 1 is a1. a1 is square root of 2, so it's just 2 plus square root of 2. Okay, so just leave it like this. We don't know how to simplify it. Okay, and then a3. a3 is a 2 plus, n is 3. 3 minus 1 is 2, so a3 is the square root of 2 plus 2 plus a2. Yes, a2. This is a2, so it's going to be very complex. So 2 plus, just put this one here. Okay, there's no way to simplify such weird expressions, so we just leave it like this. Don't simplify. Okay, and then you try a4. a4, you will see that when n is equal to 4, here n is equal to 4, here is a 2 plus a3, so it's going to be 2 plus a3 is here. Just copy this. Well, be careful about what you copy. Just copy this expression here, a4. Okay, so that's the recursive sequence. So you don't worry what is the value, what is the value of each term. So far, we don't worry about the real value. We just worry about how to write the terms correct. Okay. Okay, so this finished the section 13.1. Now let's move to 13.2. 13.2 is a arithmetic sequence. Arithmetic sequence. What is the arithmetic sequence? Definition. An arithmetic sequence may be defined recursively as a1 is a, some number, then an minus 1 is equal to d. Okay, or a1 is a, an is an minus 1 plus d. The same thing, you just move it to the other side. So this is an arithmetic sequence. Arithmetic sequence basically just means the difference of two terms is a constant, or every time you just add a constant term to the preceding term. Okay, and here a, you have two numbers, a and d. A is called the first term. D is called the common difference. The common difference. Okay? Let's see. Example. So we have, for example, 2, 4, 6, 8, 10, 12. This is an arithmetic sequence. Every time you just add 2, add 2, add 2. So the common difference is 2, right? Every time you add 2. Or it's not always increasing. Maybe you have a 10, 8, 6, 4, 2, 0, -2, -4. This time that common difference becomes negative. So here you actually add a negative number. You add a positive number. A is equal to 2, D is equal to 2. You get 2, 4, 6, 8, 12. It goes up. But if you have add a negative number, A is 10, but D is -2. Every time you add a -2, it means you subtract 2, right? Add a -2 is a subtraction by 2. So it is decreasing. So it's not always increasing. Arithmetic sequence is not always increasing. It can be decreasing. It totally depends on the sign of this common difference. Okay? How do we know if it is arithmetic or not? For example, show that Sn, the sequence which is 3n plus 5, is arithmetic. Show that this sequence is arithmetic sequence. Find the first term and the common difference. Okay, so those two quantities uniquely determine this arithmetic sequence. First term and the common difference. First term is easy, just the first number. So that's not a difficult thing. The common difference, if it is arithmetic, you have a common difference. If it's not arithmetic, there's no common difference. Okay, so first we have to show it is a arithmetic sequence. How do we know it is arithmetic? Sn is 3n plus 5. What is the preceding term? The preceding term is Sn minus 1. Sn minus 1 means in this place you are going to write n minus 1 instead of n. So it's a 3 times n minus 1. Don't forget parentheses. 3 is the coefficient of this index. So now the index becomes n minus 1. So 3 times the index n minus 1 and plus 5. Okay? And you multiply 3 into the parentheses. 3n minus 3 plus 5 is a 3n plus 2. Okay? So this is a preceding term. Sn and its preceding term. You do the difference. So 3n plus 5 minus 3n plus 2. Don't forget parentheses. I did observe some mistake like this. If you miss the parentheses, your computation is wrong. Okay? Don't forget parentheses. Okay. So it is a minus 3n minus 2. And 3n cancelled. 5 minus 2 is a 3. So this is a constant number. Then it means the sequence is an arithmetic sequence, and this is the common difference. Okay, the common difference is this constant difference. What is the first term? S1. 8. Okay, so when you reach this part, we already finished the proof part, and you find the value of 1 at 1, you get a common term, first term. So the sequence is arithmetic. The first term is 8. The common difference is 3. Okay, the first term is 8, common difference is 3. How? Yeah, common difference is 3, 8 and 3. Okay. Now let's see another one, another similar example. Show that t sub n, which is 4 minus n, is arithmetic. Find the first term and the common difference. Okay. How do I show it? First, the nth term, 4 minus n. The preceding term, t sub n minus 1. T sub n minus 1. T sub n minus 1 is 4 minus parenthesis n minus 1. Be careful, write parenthesis. Especially you have a negative sign or the coefficient. And it is a 4 minus n plus 1. It's a 5 minus n. Okay? We're not done. And then you compute the difference. It's a tn minus tn minus 1. You use the current term, subtract the preceding term. It's always this order. This order gives us the common difference. So it's a 4 minus n minus parenthesis 5 minus n. Don't forget parenthesis. So it's a 4 minus n minus 5 plus n. Minus n plus n cancelled. 4 minus 5, negative 1. This is a common difference d. This time this d is negative. It's decreasing. If you try it, you will see it's decreasing. And the first term, let n be 1. So 4 minus 1 is a 3. So the sequence is arithmetic. The first term is 3. The common difference is negative 1. Okay, the common difference is negative 1. Okay, so those two examples just help us to show if a sequence is arithmetic or not. You just get the current nth term and its preceding term and do the subtraction. Okay, so our arithmetic sequence is defined recursively. Now we want to find a general term formula for the arithmetic sequence. Because a general term can directly give us the nth term. Like for example, if you want a hundred term, the hundredth term, so you just plug in n equal to 100, you can directly write the answer. You don't have to every time you add d, add 100 times of d. That's not an easy job, right? So let's try to find the nth term, the general term. Let's see the process. First term, a. Second term, a plus d. Third term, the second term, continue plus d. So every time you add d, so this is a plus 2d. Fourth term, the previous term plus d is a plus 3d. Right? You see the pattern? If you don't, let's see. A5 is a4 plus d. It's a plus 4d. So you see here, if you have 2, then there's a d. You have 3, there are 2d. You have 4, there are 3d. There's 5, you have a 4d. So if we have an, you will expect here is n minus 1 times d. Right? It's a preceding index, preceding integer. N, its preceding integer is n minus 1. So an is a plus n minus 1 times d. A is a1. So we write the formula like this. It's a first term plus n minus 1 times a common difference. So that's the theorem. Nth term of an arithmetic sequence. Nth term of an arithmetic sequence. Right? It is a sub n. The nth term is equal to the first term plus n minus 1 times a common difference. Okay, so this is a formula. Let's see how do we apply the formula. Find the 41st term of the arithmetic sequence 2, 6, 10, 14, 18, and so on. We're looking for A41, 41st, A41. It is equal to A1 plus 41 is n. So 41 minus 1 times d. What is A1? First term, A1 is 2. 41 minus 1 is 40. What is a d? D is a common difference. You check it. 6 minus 2, 4. 10 minus 6, 4. 14 minus 10, 4. 18 minus 14, 4. So d is 6 minus 2 is equal to 4. 4 times 40, 160, plus 2 is 162. So this is the 41st term of this arithmetic sequence. Okay, so this is the application of a nth term formula for the arithmetic sequence. Another example about this nth term formula. The 8th term of an arithmetic sequence is 75, and the 20th term is 39. Okay, so we know two terms from an arithmetic sequence. Okay. A, find the first term and the common difference. Find the first term and the common difference. A's term, A8, is A1 plus 8 minus 1, 7D. Right? By the nth term of arithmetic sequence, it's the first term plus 8 minus 1, 7 times D. It is equal to 75. 20th term, A20, it is A1 first term plus 20 minus 1, 19D is equal to 39. Okay, so you have those two condition. You're going to solve for A1 and D. First term, common difference. How do you solve it? You use either one, ln 1 minus ln 2 or ln 2 minus ln 1. The reason is that if I do subtraction term by term, I can cancel the A1. So for example, I do ln 1 minus ln 2. So A1 minus A1, nothing. 7D minus 19D is negative 12D. Is equal to, I'm going to do the subtraction on the left side and on the right side. You still have the equality, okay, at an equation. 7D minus 19D is negative 12D. 75 minus 39, what is this? Either 36, yeah. Okay, just subtraction. And the negative 12D is 36, so D is negative 3. Right? You get D equal to negative 3. The common difference is negative 3. When D is negative 3, you plug in here. You get A1 plus 7 times negative 3 is equal to 75. It's a negative 21, so A1 is 75 plus 21 is equal to, what's this, 96. So the first term is 96. The common difference is negative 3. Okay, so when you get the D, you can either use the first equation or use the second equation. It doesn't matter. You will get the same A1 unless you make some computation mistake. Otherwise, you should get the same thing. Okay, so that's the first part. Second, give a recursive formula. For the sequence. Recursive formula for the sequence is A1 is here, 96. AN is AM minus 1 plus negative D plus D. Okay? It's always the preceding term plus common difference. Here is always addition, but you just add a negative number. Okay? What is the nth term of the sequence? Nth term of the sequence is A1 plus n minus 1 times D. This is the nth term of the arithmetic sequence. It's already arithmetic, so it says A1, what is A1? 96. N minus 1 times D. D is negative 3, so times negative 3 minus 3 n minus 1. And if we simplify it, this is a simple number, just integer, simple multiplication, you are going to simplify it. So 96 minus 3n plus 3. So it's a 99 minus 3n. So we can verify it. When n is 8, 3 times 8 is 24. 99 minus 24 is 75. When n is 20, 3 times 20 is 60. 99 minus 60, 39 is correct. So this is answer. Right? This is the answer. That's a way to that's examples related to the nth term formula for the arithmetic sequence. And when we have arithmetic sequence, we want to add them because it's a special, it's a simple and a special. The an is a1 plus n minus 1 times d. We want to add them. How do we add them? Let's check. a1 plus a2 plus a3 plus up to an. This is sum, right? It's a sigma. If we want, we can write like this. But this sigma notation is not important. Let's try. a1 is a1. a2 is a1 plus d. This is a2. a3 is a1 plus 2d. a4 is a1 plus 3d. Up to an is a1 plus n minus 1 times d. Okay, we just write each term by the nth term formula. Okay, now let's study it a little bit. How many a1 do we have? This is 1, 2, 3, up to n. So you have n copies of a1, so you get n times a1, n times a1. And next, here you have a d, here you have a 2d, here you have a 3d, up to the last one you have a n minus 1 times d. Alright, so first I separate a1, you have n copies of a1, and second I collect all the d's. First 1d, 2d, 3d, 4d, 5d, up to n minus 1d. Okay, that's what I did. N times a1 is already simple enough. So here, this one, I'm going to write it by the sigma. K from 1 to n minus 1. The coefficient is from 1 to n minus 1, so the top number is n minus 1. It's k times d. K times d. D is a constant, so you can move d forward. K from 1 to n minus 1 of k. And let's recall the, where is the formula? Where is the formula? Formula is here. You see, one sigma is from 1 to n. It's n times n plus 1 over 2. And this place, sigma is from 1 to n minus 1. So when you have n, you write n minus 1. Then n minus 1 plus 1 over 2. N minus 1 plus 1 is n. So finally you get your formula. How they write it. It is it's like this. So this is the formula. This is a formula. And in the textbook, they factor out this n. You have here you have n, here you have n, and you have this 1/2. We factor out n over 2. Then this first part becomes 2a1 plus n minus 1d. Okay, 2a1, I factor out n, factor out 1/2. Here there's no 1/2, so I just divide by 2 and multiply it by 2. So that's why I have a 2a1 and n minus 1d. n minus 1d is here. This is a formula you will read from the table, from the theorem. And another thing, 2a1 plus n minus 1d. I write it as a1 n minus 1d. What is a1 plus n minus 1d? That is an. So this sum is a1 plus an also, this part. So, right? This sum is also the a1 plus an. So to summarize it, we get theorem an is arithmetic than the sum of the first n terms sigma k from 1 to n a k. It is equal to, you can write it this way, n over 2a1 plus n minus 1 of d. This is one of the formula. You read it, it's a formula 3. Or it can be equal to n over 2a1 plus an. It's here. It's a formula 4. This is a theorem on page 951. The sum of the first n terms of an arithmetic sequence. Okay? Well, let's use it. Let's try to use it. Example. If an is 3n plus 5, first, it is arithmetic. How do we know it is arithmetic? You just figure out what is an, what is an minus 1, the preceding term. We did this computation in the previous examples. You check it, and then an minus 1 is equal to 3. This is arithmetic. Once you have a common difference, it is arithmetic. Okay, and the initial term a1 is 8. n is 1, it's 8. Then the sum sigma k from 1 to n a k, the sum of the first n terms, it is equal to, you have two ways. Either you write it as a n over 2 times first term plus n minus 1 times common difference. Or you have first term plus nth term. First term plus, this is nth term. an is nth term. a1 plus an. This is a1 plus an. This is 2a1 n plus 1 times d. N minus 1 times d, my bad. Okay? So you can examine it. 2 times 8 is 16. 16 here. Yeah. 16, this is n over 2. 16 plus 3n minus 3. So it's a 3n plus 13. Here is also 3n plus 13. This is 8 plus 5 is 13. The same number. So you can either use this or use this, but eventually you will get the same formula like this. Okay? That's the example. How do we find the sum of the first few terms? Next, Let's have some concrete numbers. Find the sum. 60 plus 64 plus 68 plus 72 plus dot 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 up to 120. This is an arithmetic sequence. Every time you add 4. So if we want to add them, you know that the sum is equal to first term plus the last term times how many terms you have, and then over 2. How many terms do we have here? Okay, let's check how many terms. This is A1. So A1 is 60. Then I don't know n, so AN is 120. AN is an arithmetic sequence. AN is A1 times n minus 1 times plus n minus 1 times D. D is the difference, is 4. So it's a 60 plus 4 n minus 1. It is equal to 120. You solve this equation, you look for n. Let's try it. Okay, you move 6 to the other side. It's 60. 120 minus 60 is still 60. And divide by 4. 60 over 4 is 15. So n is 16. So there are 16 terms. So the Sn, you put it here. So 60 plus 120 is 180 times 16 over 2 is 8. 18 times 8. Okay, it's 1440. 1440. Okay, so that is the answer. Okay, so this is a chapter, section 13.2. The section 13.2, we have arithmetic sequence. This is arithmetic sequence, the nth term, and the recursive term. Recursive definition is like this. You have two definitions, and you have the sum. You have the sum of the first n terms. Okay, so those are the most important formulas for the arithmetic sequence. You're supposed to handle them, and you can apply them to the exercise. Okay, send me email if you have questions. Okay, we finish this section. Thank you.